Okay, so welcome everyone to this week's One World seminar. We're very happy to have Peter Richtarik. So Peter is a professor of computer science at KAUST. Before that, he was associate professor in mathematics at the University of Edinburgh. He's had various visiting positions, such as at the Moscow Institute of Physics and Technology, at University Catholic de Louisiane, I'm probably mispronouncing that, at Berkeley. And prior to all of that, he did his PhD in Cornell. Won several awards, including Best Paper Awards at NeurIPS and SciGest. He's also won a Distinguished Speaker Award at the 2019 Conference on Continuous Optimization and an IMI Leslie Fox Prize. So we're very happy to have Peter talk this week. We'll be speaking on the resolution of a theoretical question related to the nature of local training in federated learning. So please, over to you.
Yeah, thanks a lot for having me here. So I'll talk about mostly one paper that you can see here at the bottom called ProxSkip. Yes, local gradient steps probably lead to communication acceleration finally. So it's a weird title, I admit, so feel free to laugh. We had a laugh as authors coming up with the title ourselves, so too many exclamation marks and so on and so forth. Seems quite unscholarly, but we just felt we wanted a funny title for this one. But in the end, I might comment on some other extensions. So since the title is so weird, we actually felt the need to include a subtitle, which would sound more scholarly, and that is this one, ProxSkip Breaking the Communication Barrier of Local Gradient Methods. This is joint work with these three wonderful co-authors, Konstantin Mishchenko, who was a PhD student in my team. At the time this idea really started and first results were obtained, and then this was finished off when he moved on to postdoc position at INRIA. And Grisha Malinovsky, who is a PhD student in my team at the moment, and Sebastian Stich, who is a co-author and a friend and visitor. So here's the outline of the talk. I'll first introduce the area of federated learning a little bit, because I do not know how many of you know what this is. It'd be a very brief, gentle introduction into roughly what's going on. And then I'll talk about local training as a certain algorithmic idea or tool which does something and is not clear what it does and why it does it. And this is the whole reason why we've written this paper and why this talk exists. And then I start talking about how we actually approach the problem from an analytical point of view, and that's what all of these 3 to 7 parts here are about, the actual meat of the talk, and then I'll have maybe just a couple slides on extensions. So what is federated learning? So federated learning is really something like this, and I stole this image from a Google blog from 2017, which by the way is the same year when I left to Edinburgh and joined KAUST. So the first federated learning app that was shipped as a product to phones was this next word prediction. So the idea is that there are millions of mobile phones out there, actually more than millions, but lots of mobile phones, and everybody is using this Gboard or Google keyboard on these Google devices, Android devices, and people are typing something in there. Maybe we can save them a little bit of time if we can complete the sentences or words that they start typing, because of course it's cumbersome to be typing on these artificial keyboards on the phones. However, in order to build such an engine, such an app, one needs to train it across the data which is stored on these mobile phones, and it's not enough to train such models on the data stored on a single phone, because a single user might not be sending so many emails or writing so many pieces of text that a powerful enough model could be built that would do that would be able to do this task. But if we train across the data stored across all of these devices, maybe millions, tens of thousands, and so on, then maybe enough data is there so that you can build such a model. So this is the basic idea. So federated learning kind of started through collaboration between my team and the Google team of Brendan McMahon. So now it's already a number of years, so 7 years or so. Why am I mentioning this? I know now because the student that started this with me, so Jakub Konieczny, he then joined Google and has been very active, further pushing the system side, algorithmic side of federated learning. And Kostya Mishchenko, who is the latest student graduated from my team, he's the co-author and first author on this paper. So here's the Google AI blog from 2017, which in fact is 1 month after I joined. This is April 6th, I joined roughly in March, which mentions some papers. In fact, it mentions 4 papers as the foundational papers of federated learning. So 2 of these are in collaboration between me and Google Lab, but I really want to focus on this first one, which is communication efficient learning of deep networks from decentralized data. So this is one of the most famous and most highly cited papers in federated learning, where the idea of federated averaging was really introduced to the world of federated learning. And this is where this local training idea shows up. The idea is older than this, so it was not really discovered in this paper. It's at least actually 2 decades or more older, but really became famous because of this paper. Okay, I really had this slides prepared for some different audience, but I want to say that this really influenced a lot the work that we do in my team. So these 2 papers that I mentioned here, they're right now my most cited papers, and we quite a bit focus on federated learning right now. I would say that at least half of the work that we do is somehow in one way or another related to it, and there are many interesting mathematical questions, algorithmic questions, systems type questions, and so on over there. So federated learning has started transforming industry. It's used already in many companies and so on and so forth. And what I really want to focus on here is to say that many things need to be tackled in federated learning. So many questions, many tools exist to tackle them. And I will only focus on a single one in this talk. So I will not talk about personalization at all, or differential privacy, or partial participation, and so on. I will only focus on this idea of local training, which is a key component in the federated learning averaging algorithm by McMahon and co-authors that I highlighted before. And the reason behind this is because this is, I would say, one of the most misunderstood or not enough understood ideas in federated learning. It's very, very powerful, used in all the software. However, we don't have good theoretical understanding of what's going on. So what is it? What is local training? So I'll start with this paper that I highlighted by Brendan and his co-authors. Very influential paper. So this is this one from that slide. And the idea is really something like this. So you start with gradient descent, then you implement in a distributed fashion, which still be actually gradient descent. This will not be a different method. It will be just applied to a certain problem, and you would interpret the method as distributed method. And then we add the locality to it, and that's what distributed local gradient descent would be. And this is the most basic local gradient method, or method that does local training. So I'll go through this. I guess everybody knows what gradient descent is, so I'll not spend any time on this. This is just a very quick picture. We try to follow this gradient flow in a discrete manner down the hill. What would distributed gradient descent be? So we want to be now solving the problem of minimizing the average of many functions. And the idea here is that N is the number of clients or nodes or workers or these mobile phones. This could be millions. And these D would be the number of parameters or features or weights in the neural network that you wish to be training. And FIs are the aggregate losses across the data stored on these individual devices. So Fi would be the aggregate loss over all the training data on device I, and we will not assume, which is unlike much of the literature on federated learning, any type of similarity between these distributions. And I'll comment on this a little bit later. So this is the problem. Another question is, okay, how would you implement the gradient descent for this problem where you want to minimize the average of any function? So obviously, gradient of average is just average of gradients. And now the basic observation, which is completely trivial, is that each machine, each client or phone can compute a gradient over its own loss function or its own local data, but the average really necessitates communication. So only if the machines are somehow connected, the average can be computed. And this is very time consuming because these phones are typically connected to this orchestrating server through some very weak links. And that is really the bottleneck of the entire system. So I will now write down a different way of implementing gradient descent. So actually the distributed way. So this is how it would look like from the point of view of the workers. So let's say we have 3 workers. We have some server that will be there only to do the averaging. So that's the whole purpose of the server. It will facilitate communication. So this is how this gradient descent gets started. Everybody receives a current copy of the model from the server, and then creates a copy of that copy so that these copies can change, and takes a gradient step with respect to the local data. So notice that everybody takes gradient descent step with respect to different function because this is the function that they own and the data that they own. So immediately these models x1t plus 1, x2t plus 1, and so on, they're different. And then these models get shipped to the server, and this is the costly part. And the server just averages them, that's it. However, average of these models, this is the same thing as performing the gradient descent step. This is very easy to see. And then this model xt plus 1 gets broadcast back to the workers, and the process is repeated. Now, this broadcast is very expensive, and the upload, the orange arrows, are very expensive, and this is really the problem here that this idea of local training is trying to tackle. And the idea really is, what if, let's say, this one gradient step locally on each worker takes a second or a minute or something like this, but then you're uploading for an hour because you're connected through a weak link, and you're uploading a d-dimensional, so maybe million-dimensional model. So this clearly seems like an imbalanced system, and it seems to be very inefficient. So the idea of local training would be just do more work before you communicate, because if you do work which only takes a minute and then you communicate for an hour, that really looks, even if you don't do any mathematical analysis, this really looks like you're not doing the right thing. So local gradient descent, this local gradient descent is the same method, except for one change. You don't take just one gradient step, but then you take another gradient step, yet another gradient step, and so on. And you take a certain number of gradient steps, and only after that you communicate. And as I said, the idea really is that maybe this local training, this capital K local gradient steps, will now take maybe an hour. This will be roughly the same amount of time as you would communicate. So maybe you have a more balanced system, and maybe this is going to help. However, this seems to be wishful thinking. This is not gradient descent anymore. It's a different method. That's why we would call it local gradient descent or distributed gradient descent. And it might not even converge. So when it was first proposed, this was a heuristic, and people looked at it, and it helped quite a bit. But sometimes you could observe that it doesn't really work the way you would want it to. So these models get sent to the server averages, sends back. So this is distributed local gradient descent. And now the big mystery behind this method, or methods which work in a similar fashion, so that they perform multiple gradient type steps before communication, the big mystery is that in practice, this helps to reduce the number of communications needed to train the model by factors between 10 and 100. So huge factors. So nobody in their right mind would run just gradient descent. Everybody would do something like this. However, there's no theory which predicts that this actually should happen. And that's really the issue that we wish to tackle. So let me mention this, unpack this a little bit in a little bit more detail. So I would say, of course, gradient descent dates back several centuries. then one can say that local gradient descent was first proposed roughly 30 years ago by O.V. Mangasarian in this paper, but you have to close one eye to see local gradient descent in that method. But definitely federated averaging, and a couple of years before, 2015, 2016, there were already some papers where this idea of local training before syncing the parameters was pursued and proposed, but definitely became famous in 2017 in this paper by McMahon and Cotters. However, when they proposed this local training, this was a heuristic and there was no mathematical convergence analysis done in the paper. The paper was purely empirical. However, the gains were really, really impressive. Then it took some time for people to be able to analyze this method without assuming that the functions are very, very similar. So I'm kind of skipping some development between 2017 2020, where first papers appeared which managed to analyze local gradient descent. However, the analysis had to assume that the functions are similar or maybe even very similar. And the idea there is clear. If the functions are identical, then there should be no need for any communication whatsoever because everybody has all the data they need to train the model. So you just take infinitely local steps, you solve the local problem, and everybody get the same solution if the functions are the same. And if you don't deviate from this too much, if the functions are quite similar, then local steps should help. However, practitioners saw that local steps help even if the functions are arbitrarily dissimilar. And there was an open problem at that time in 2020 related to the convergence of local gradient descent without assuming any type of homogeneity. And this is what we managed to solve with Ahmed Khaled and Konstantin Mishchenko in 2020. So why does local training really work? If you look at it from a pragmatical point of view, if you run the method, what do you observe? So you observe something like this. So if you run just one local step, which means you're really running gradient descent, you get this type of convergence. So let's say this is some kind of L2 regularized logistic regression, such some baby problem, toy problem, linear convergence, because this is strongly convex L-smooth function. However, clearly it's suboptimal if what you want is a solution which is not very highly accurate. So if you want solution which is when the accuracy is 10 to the power minus 6, then it makes sense to run gradient descent. But if all that you want is 10 to the power minus 3, let's say, maybe you should take 32 local steps, and then you converge there with many, many fewer communication rounds. However, then you also get stuck around that accuracy, and the method cannot really improve. So this is what people observed, but there was no theoretical explanation for this phenomenon. And also the issue here is that why do these methods get stuck? Can we get them unstuck somehow? So this was the problem that was open at the time when we worked on this work. So this problem was resolved in this scaffold paper by Sai Pranit Karimiredi and co-authors, where they introduced the idea of drift reduction. And there's some other papers, including something from my lab and a Fedlin paper by Mitra and co-authors, which propose some alternative methods which achieve the same theoretical effect. And the effect is that the method will not get stuck. It will continue at a linear rate. However, what all of these methods have in common is that the theoretical complexity, communication complexity, is not better than gradient descent of any of these methods. So of this method, the local gradient descent method, the theoretical communication complexity is even much worse than gradient descent, unfortunately. So while we're quite happy that we got some analysis, of course, we got the method that is even worse than gradient descent, and that is very dissatisfying because in practice, the method is much, much better than gradient descent. So clearly we're missing something. And one of those pieces of the puzzle was exactly this drift reduction, which came later. However, even once this drift reduction idea came up and these methods were created and the analysis was done, still the analysis said the method is worse than gradient descent, or maybe at best matches the same communication complexity. And so as of this year ago, 2021, still there was this open problem do these local steps actually help to reduce the number of communication rounds or not? In practice, it looked like yes. In theory, the answer was clearly no. And this is what is really the key, the starting point of the paper and of the talk here. So is the situation really hopeless? So there may be some examples where it doesn't really help, or can we really prove that the local training helps? So this is really the main motivation for this talk. So I guess I'll just pause for a moment in case anybody wants to ask some questions about these first two parts of the talk. I'll click on the chat. There's nothing in the chat. I'll have another sip of coffee in case somebody wants to say something. Matthew, I'm not frozen. I'm just waiting a little bit, giving people time.
Yeah, it's fine. Yeah, it's a good idea, I guess, to let people have a chance if they're writing.
All right, so I move on. But do not hesitate to interrupt me anytime. So I'm going back to this problem formulation, which is the main optimization formulation of federated learning. It's a standard finite sum minimization problem. However, in order to shed some light on this nature of local training and federated learning, we had to reformulate the problem into a form which is also standard in the distributed training and distributed optimization literature, but not very standard in the federated learning literature. And the reformulation is you first give some freedom to every model on each client, because you say this is xi, not x. So now every client can have their own model and they can differ. But then you take the freedom away immediately by introducing a penalty which is going to be infinite if the models are different and zero if they're the same. So this is mathematically the same problem. Now, obviously, this problem can be generalized further because this is just an indicator function of a certain closed convex set, which happens to be this set. So we can maybe work with penalties, which are indicator functions of arbitrary closed convex sets. And one can go to even one high level of abstraction, where we notice that this kind of an indicator functions of closed convex sets are proper closed convex functions. And the function is closed and convex, even if its epigraph is a closed and convex set. So the formulation we wish to really work with is more abstract than what federated learning really wants us to do. And it would be just the formulation minimize some smooth, nice functions, smooth and strongly convex function fx, and some proper closed convex regularizer. So this is the standard composite optimization problem in the optimization literature. Okay, and now the main observation here is that there is a very well-known method called proximal gradient descent, which solves this problem, which everybody knows, and it works in this way. So under the assumptions, we'll work under these assumptions that the function is L smooth and mu strongly convex, which means that this Bregman divergence is lower and upper bound in a particular way, and we'll assume the regularizes proper closed convex and also proximal, which means that the proximity operator, which is written here, has a closed form solution. So we don't have to really run some subroutine to evaluate it. So once these assumptions are in there, we can run proximal gradient descent. And proximal gradient descent first takes gradient step, pretending that the non-smooth proper closed convex function doesn't exist at all. However, once this gradient step is taken, one takes the proximity operator, applies the proximity operator to this. So this is a particular instantiation of the forward-backward method, where this is the forward operator, the gradient operator, and this is the backward operator, the proximity operator. So everything is pretty nice and standard here, no problem. But the observation that I really want to highlight here is that when you compute the proximity operator of this very particular set that we work with, so this kind of a function, which is indicator function of this particular set, that proximity operator just means averaging. You just average all these xi's. That's what you need to do. So evaluation of the proximity operator here means averaging, but this is averaging across the models of the clients, which exactly means communication. So the issue of avoiding communication has something to do with the issue of avoiding the computation of the proximity operator. So once we think of it at this abstract level, we'd like to come up with an algorithm which looks like proximal gradient descent, but which tries to avoid the evaluation of the proximity operator. And this is why we call this algorithm ProxSkip. We try to skip the proximity operators very often so as to avoid communication. And when you skip the proximity operators completely, and you only do this forward passes or you apply the gradient operators, that means, since this is in the ND-dimensional space, this means that everybody just keeps taking local gradient steps. Okay, so this is really the idea. I want to just recall the basic result for proximal gradient descent. This will help us to contrast it later to our result. So the result says, and this is a very well-known textbook result, if the number of iterations is going to be at least the condition number times log 1 over epsilon, then you have an epsilon solution to your problem for a certain step size. So this is all standard. So now, what we want to do, as I mentioned, we want to skip the proximity operator somehow, but still get an algorithm which converges, which solves the problem. And you can't simply just skip it fully and do nothing to correct for it, because then the method will be divergent. So we have to do something.
There's a couple of questions in the chat, if I can interrupt you.
Yeah, absolutely.
So the first question is this idea related to gradient sliding?
Yeah, it is. It is something like gradient sliding, that's right. But we're not sliding the gradient, we're kind of sliding the proximity operator instead. So there's like proximity sliding, you can call it if you wish. So yeah, it is related.
Okay, and then the second question is, why is it expensive if it has a closed form solution?
Right. So here it's going to be expensive not because it's computationally expensive, because I said that the proximity operator of this indicator function of this set right here simply is averaging. So that's the simplest possible operation you could do. However, it's expensive because all of these models are on different clients, on these different phones. So this is on phone 1, this is on phone N. And in order to do the averaging, you have to communicate. So it's the communication that is expensive. If all of the data was on a single machine, it'd be the cheapest operation you can possibly do. But this is why it's expensive.
Thanks.
Okay, so in order to explain what ProxSkip does, I will first suggest an approach where we skip all the prox evaluations, all of them. So there won't be a single one, and we'll have a very, very efficient method, or at least it might look like that, where there won't be any communication necessary whatsoever. However, the method will be utterly useless and not implementable at all. So why am I mentioning it? The reason is because it will really be an inspiration for the approach 2, which is really the ProxSkip approach. So this first point of view will really help us to design the method. And the second approach is really then the ProxSkip approach. So let's start with this simple and useless approach. So the simple approach is this: forget completely about the regularizer, about this penalty, this zero infinite penalty. But instead, perturb the function, the f, this is the average of those functions in the Federated Learning application, by a very particular linear function. And the linear function has gradient equal to the gradient of the smooth function f at the optimal point of the composite problem. So of course, you don't know this h star, because you need to first solve the composite problem, which is what we want to solve, minimize f plus psi, to find x star, and then to evaluate the gradient of f at x star in order to find h star, right? So this is chicken and egg problem. You don't know this perturbation, but let's see what would happen if we knew it. We don't know it. I don't pretend I know it, right? We don't know it. What would happen? Well, it turns out that x star just happens to be a solution of this problem. And the reason is you just write down the first order optimality conditions, set the gradient to 0, and under some assumptions such as strong convexity and so on, where the solution is unique, you'll see that X star actually is a solution of this problem. So you can solve a linearly perturbed version of your original problem without adding the regularizer at all, and that will actually solve the original problem. However, we don't know the perturbation. So the next question I want to ask and answer, what would gradient descent look like if we applied it to this problem? Well, what it would look like this, because the gradient gets perturbed by this H star, by the gradient of the linear perturbation. And this is what you would run. And if you apply this now to that lifted formulation in this lifted ND-dimensional space, this would simply just mean everybody keeps doing local gradient steps and they never sync to average to communicate. So everybody just computes these local gradient steps over and over again. No communication is necessary, and everybody will then converge to X star magically. If we knew this magic perturbation H star, which we don't know. Okay, so this method is something like an idealized ProxSkip because it skips all the communications completely. It never does any prox evaluation, but it assumes that magic happened, which is that we know H star, which we don't know. Okay, so now what do we do? The basic idea behind ProxSkip is to somehow learn this perturbation H star on the way, but learn it in such a way that we don't have to access the proximity operator of psi very often. That's really the idea. Okay, so not at every iteration, certainly, as rarely as possible. So we replace the H star by HT. So our method ProxSkip would look just like this. Okay, so just like this, we just replace H star with HT, and we hope that we can generate sequence of HTs which will converge to H star. And later on, we will prove that it converges to H star. So that's the desire. And maybe we can learn this H star with only occasional access to psi, as I mentioned. So let me now go to ProxSkip proper. So from a bird's eye view, the method looks like this, which is identical to what I wrote before, apart from this hat on xt plus 1, because sometimes the hat is removed and sometimes actually there. I'll explain this in a minute. So this is the current model. This is the shift. This is some kind of a temporary model. And once you take this step, what we do is that we flip a coin. After every single step, we flip a coin. And with some very, very high probability, we do something. And with very small probability, P, we do something else. So what do we do with very high probability? With very high probability, we say that the next shift is the same as the previous shift. And we just drop the hat from xt plus 1. Okay? So if you compare this method to this method right here, that's the same method, right? So with very high probability, just keep doing this. With the fixed shift ht, which you don't change. You just keep doing this, right? Okay. But obviously that cannot work on its own because you never change the shift and you didn't guess the shift correctly. It's not H star from H0 is not H star. So this will converge to some strange point if you never change the shift. But with very small probability, what we do, we actually change the shift, this ht plus 1. We change the xt plus 1 in a certain way, and we do this through the evaluation of prox. So in the federated learning application, we do some communication, but we do this with very small probability. So from the federated learning point of view, what happens that everybody keeps taking local gradient steps for a very long time because p is very close to 0. And then at some point, what happens is that communication happens and this shift, this yellow vector changes and everything is restarted. So this is how it looks like. And this is really exactly the ProxSkip method if you fill in these 3 question marks. So this is, I'm not hiding absolutely any detail of the method except for these 3 question marks. Once these 3 question marks are there, this is exactly the ProxSkip method. So I think this is a good time to pause in case anybody has some questions. Okay. So Gesualdo is asking some question. Yeah, well, I'm not aware that George Land's sliding does this. So I looked, I even have the book here. I don't think that this is what he does. But maybe you can point me exactly to some paper somewhere. So he has these three terms: smooth and something where you can compute subgradient, and then proximal one. But he's really skipping gradient evaluations for the smooth term. Okay. Any other questions? Yeah, but at the same time, Gesualdo, congratulations on your recent paper with Dmitry Kovalov and others on a new version of gradient sliding, which is very nice. Okay, I'll wait because I think at least, so this is important slides. I want to wait a bit. All right, I think I waited enough. So that means you are really serious that you don't have questions, which is great. So let's move on. So this is how the algorithm actually looks like. So when these three question marks are filled in, but I don't want to spend really time explaining what these question marks do. All that I want you to really know about the method for the purposes of this talk is that this is it. And somehow these three question marks can somehow be filled. Okay. So what's the theory behind ProxSkip? So the theory is this, and now keep in mind the theory of proximal gradient descent, which I mentioned before, which doesn't have this 1/p² term. So proximal gradient descent. Okay, something just happened here. Oh, they're cleaning the windows in a rough way over here in my office. Okay, so if the number of iterations is at least condition number, and the maximum with 1/p² times log 1 epsilon, then you find an epsilon solution to your problem in a certain sense. Now the probability P is this tiny probability of evaluating the prox. Okay, so now what I really want to stress here, and this means some certain Lyapunov function is epsilon small. And I'll say what that Lyapunov function is in a moment. But what I want to stress is that here immediately we see that something nice really happens with the method. And the reason is this. It's very clear that P being 1 is not optimal. So evaluating the prox every time is clearly not optimal. And the reason is because if P is 1, then you take in the max of some condition number, which is typically large, and 1, and clearly the maximum is going to be the condition number. So this is exactly the rate, the convergence rate of gradient descent or proximal gradient descent. But as soon as you decrease P to something smaller, if you are not far away from 1, the maximum of these two quantities will still be this blue quantity. But that means that you get fewer proximal evaluations completely for free. Nothing changes with the bound on T. All that happens, you just have cheaper algorithm because it does fewer prox evaluations. So you may ask, what is really the optimal P where you should stop? Where it turns out you should stop exactly where L over mu is equal to 1/p². So you should choose the probability P to be actually 1/square root of the condition number. And if it's this, then these two quantities became the same. And then this means that we really skip the proximity operator very often. And that's how we improve on proximal gradient descent. So the Lyapunov function is this. It includes the original distance to the solution that was part of the theorem of just proximal gradient descent, but it also includes this dual information of convergence of the shifts to the optimal shift. So remember the idealized ProxSkip method, which skipped all the proxies and never actually communicated, which used this optimal H-star shift. So that one would use this H-star shift, and this theorem really shows that our shifts converge to this idealized perturbation. So, so our wishful thinking was realized. So these HTs really converge to A star and XTs converge to X star. And XTs converge to X star in a faster way in terms of the number of proximity evaluations, precisely because these HTs converge to H star and with just few proximity evaluations. Okay, so this is it. So let's look at how to solve for the optimal P. If you want to find the optimal P, it turns out you have to minimize the product of P and the number of iterations. Why? Because this is the expected number of prox evaluations. This is the simplest expectation anybody can compute because T is the number of iterations. And with probability P in each iteration, you do a prox evaluation. So the expected number of prox evaluation is exactly PT, right? So we calculate what PT is, and it turns out it's this quantity, is the maximum of these two times log 1 of epsilon. And you can see this is a maximum of a linear function of P and 1 over P, which is a nice convex function of P. So this is a maximum of two convex functions. It's a convex function. And it's univariate, and you can easily minimize this in P. And the solution will exactly be 1 over square root of the condition number. And here's just a very simple numerical example where the condition number is 2. And one can clearly see where minimizing the maximum of this linear increasing function and this 1 over P function. And the maximum is minimized exactly at this point right here, where they intersect, and which happens to be exactly 1 over square root of 2 in this case. And the 2 is the condition number. So 1 over square root of condition number. So if we summarize everything, that then we have this formula for optimal probability with which to skip the proximity operators. And the result of it is that we have a method whose number of iterations is still the same as that of proximal gradient descent. Nothing changed there. Still the same number of iterations. The same number of gradient evaluations. Nothing changed there. What changed is the expected number of prox evaluations is much smaller. And this is because in between two prox evaluations, we take square root of kappa local steps. So somehow it's a smarter allocations of the kappa iterations of proximal gradient descent among those that need communications and those that don't. So it turns out you can do square root of kappa local iterations, local gradient steps, before you do communicate, before you do the proxy evaluation, and it doesn't at all hurt the theoretical iteration complexity of proximal gradient descent. So this is really where this acceleration comes from. So what we really get is the first result in the literature on these local training methods, which says that local training really helps to reduce the number of communications from condition number to square root of condition number. So we get some sort of an acceleration effect of Nesterov type. We go from condition number to square root of condition number. However, this is not Nesterov's algorithm. This is a different algorithm where the acceleration happens through local training. And I have to stress that acceleration only happens for the number of communication rounds. It doesn't happen for the number of gradient evaluations or iterations. So you can think of this as some sort of semi-accelerated method, if you wish. Okay, so we have this table in that paper which summarizes the previous state-of-the-art results in the literature on local training. So this gradient descent method, clearly that's a method which doesn't do any local training. It just takes one local gradient step, and the complexity is proportional to condition number. Then when we look at local gradient descent, which was this first method by Ahmed Khaled, Konstantin Mishchenko, myself, which analyzes local gradient descent under arbitrary heterogeneity of the functions, we got a sublinear result, which is even worse than gradient descent, but we're happy that at least we can bound things somehow, and we can show that the method actually works. It will not diverge, it will converge, but it is worse than gradient descent. Then there were these methods which resolve the issue of convergence, which is slower through the drift reduction. So those were these three methods, scaffold, S-local, GD, and Fedlin. So they improved this back to O kappa However, this kappa is at best equal to this kappa. So I'm kind of cheating a little bit. The notion of kappa is not everywhere exactly the kappa here. It's a little bit worse somehow. But let's say that this is the same kappa. So at best, this rate matches the rate of gradient descent in terms of number of communications, which means it doesn't really show any advantage coming from local steps. In our work, we have this general probability with which we evaluate the proximity operator with which we communicate. And the number of communication runs actually is p times kappa plus 1 over p for any probability p between 0 and 1. And now we can optimize over p just by minimizing this quantity. The optimal p happens to be 1 over square root of kappa, which means that the expected number of local gradient steps is just square root of kappa. We take large local steps, training rate, learning rate, 1 over L, and we get square root of kappa communication complexity. Okay, so I think this is another good time to pause before I move on to experiments. Okay, now I'm looking at the participants. I can see Bubakar here. Hi, Bubakar. I guess people cannot say anything, right?
I think people should be allowed to unmute themselves. If you want to, there are some questions in the chat appearing, which I'm happy to kind of read out.
Okay.
Is, can the error rates showed in the beginning before part 3, they think that range between 10 to the minus 3 and 10 to the minus 8 be illustrated on simple test functions, so that this phenomenon, how the rate change depends on how long each individual work compute steps, can be isolated in a simple setting of how convergence.
Yeah, I'm trying to understand the question. Can we unmute this person so that I can get some clarification on what this means?
Yeah, do you want to?
I'm not sure if I understand the question, to be honest.
I think people should be able to unmute.
Okay, the person is here. Hi. So my question is, right at the beginning, you had these graphs where you showed how the error rates dropped. Yeah. So are these coming from an experiment, or do you have some really simple functions?
Yeah, that comes from experiment. So that was we actually run the local gradient descent method, and that's what we saw.
Yeah. So, and my question is, can you reproduce similar graphs, but not from a setting where you have an actual experiment, but just functions that you define by hand, so that you can just really isolate this phenomenon in a simple.
So no, local gradient descent. So in that plot, it turned out that if you increase the number of local steps to something more than 1, which means you're going away from gradient descent, you actually run a local gradient descent, then the method initially converges much faster, but then it gets stuck much sooner, right? Yeah. So the part that it gets stuck sooner, that we can see mathematically, and we've seen it in this paper by Khaled, myself, and Kostya Mishchenko. However, the fact that it converges faster, that is not supported by theory. So already that was not clear. That is not clear why that is actually happening. But so there's some sort of strange, there's like faster linear rate can be observed there initially, but there was no theory which would say why that should happen.
Yes, but so all the individual FIs, right, that represent loss functions. Yeah. Would you have, I'm not sure if you have, but maybe you do have some example for the individual FIs, not loss functions, any other functions that illustrate the same phenomenon, just so that it's maybe theoretically simple to get a handle on them. Because if you have a loss function, then
I understand. But as I say, there was nothing of that type. So empirically, we saw this, everybody saw this, but in order to show that these local steps help, so that this initial decrease of that curve is steeper, people could only show this if you assume that these local functions are somehow similar. And that is intuitively clear, because if they're identical, then you don't have to communicate at all, and so on. So that was simply, that was unsupported by theory.
Okay.
But now we know that that linear rate should be faster because of this acceleration effect. So now we know that through this ProxSkip method, but the method had to be changed. For the original one, I'm not aware of anything like that.
Okay, thank you.
My pleasure. So I'm looking at, so Philip, maybe can you ask?
Sure.
I'd like to hear some other voice in mind, so this would be great if you could, even though I can read your question.
So you use this coin flip, this Bernoulli experiment.
Yeah.
But obviously in practice, you would maybe just want to take every p iteration.
Yeah.
Use the proximal operator. So how necessary is this randomness for the
yeah,
result?
so we don't think it's is necessary, no. So we run experiments also with the method which doesn't do that. And in fact, we discovered that if you do it that way, which is a little bit funny. So if you actually do it that way and you compare it to a certain version of scaffold algorithm, they're the same. So the method we try to improve on, scaffold, can be seen as ProxSkip, which takes deterministically many steps. However, the theory of scaffold says this is just like gradient descent. There's no acceleration. So there is some difficulty there with analyzing the method, which takes deterministic number of steps, but I don't think it's a fundamental difficulty. The randomization helps with the analysis tremendously. It simplifies things. There are no two loops in the method. It's just single, you can do single iterate analysis and so on. So the randomization helps in the analysis. But in fact, if you use deterministic number of steps, it even sometimes improves the method a little bit. So stabilizes a little bit more. So that's an open problem at the moment. However, we do have a different method, which is not ProxSkip, which takes deterministically many steps. And it also has the same theoretical communication acceleration. And this is in one of these extensions. But we're not yet able to do that for ProxSkip.
All right, thank you.
Okay, my pleasure. Evangelos?
Yes, I would like to ask you if we can apply this to sample POC or PD3O, this ProxSkip idea.
Yeah, so that's an excellent question because we did both of these. So, but not in this paper, in these extensions. So maybe
I've seen this paper.
Yeah, so let me go here. So these extensions, okay, at the end. And so let me see. So this one, I lost the pointer. I don't know. Okay, now it's here. Okay, so there's this extension by Abdurrahman Sadiev and Dmitry Kovalov and myself. So this is actually, we do, the basis of the method here is the Shambhal-Pog algorithm. And we do some modification. Yeah. So finite subnames. And we do some modification to Shambhal-Pog so that we massage it into a local training method. So we had to do some changes in the theory and in the algorithm. Actually, not very major, two main changes or two or three main changes, and redo the theory and simplify it. But then we get actually a local training method with accelerated communication complexity, and it's a prime-dual algorithm. We also have another one, which is this random prox with Laurent Condat.
Yeah,
and this is really, yeah.
You compute the proximal randomly, and you choose how you compute. You do not skip.
Yeah, well, we do skip. We do skip. So the main observation in this paper is that you can think of this skipping operator, okay, of skipping as the application of a compression operator to the proximity operator. So we compress the prox, and if the compression operator is a Bernoulli compressor, so that with a certain probability it outputs 0, and with certain probability it outputs identity divided by the probability p, so that this is unbiased compression operator, we recover ProxSkip. But the phenomenon is more general. So we can compress randomly the proximity operator, and that's how we did this theory here. So this is generalization of ProxSkip, but at the same time, we realized we can handle also some non-smooth terms and so on. So we have a more powerful, more general framework which can deal with the minimization of sum of 3 terms rather than just sum of 2 terms. So we get PDDY, prima dual Daviesian splitting as a special case, and so on and so forth. So I would definitely recommend people interested in this topic to look at this, because this is a more general framework than the ProxSkip framework. But we were not able to, we didn't know this until we thought about this carefully, what actually this ProxSkip does. And then once we realized it, we wrote this paper. Okay, so I was here and I'm checking, is there any other question?
Thank you.
My pleasure. Okay, and Philip, you have one more question there?
I had one more, but I can also ask it at the end. So that's,
yeah, I'm okay with chatting throughout. That's fine. I mean, we can even stop here. I can just show a couple of computational plots, and that's fine.
Well, then I can ask the question real quick. It's just related maybe also to the first question. So in the original example, it looked like the best thing you could do is start with very few communication, then make more communication, and so on and so forth. So in a sense, it relates to choosing this P, the probability adaptively to, I don't know, depending on the iteration or the accuracy that you currently have. So that's why I was wondering if you can.
Yeah, well, it looked like this for the local gradient descent method, which didn't have the drift reduction applied to it. And then indeed, it looked like that maybe you should start with maybe more local steps than fewer local steps, and so on and so forth, so that you can really be surfing the wave of the best case loss across all of these curves that were there. However, once you apply the drift reduction, then the rate is just linear, and that intuition doesn't apply. And in our case, it just turns out that the optimal probability has a closed form solution. It's 1 over square root of condition number, and we don't see anywhere in the analysis how it would make sense to make the P, or the number of local steps, adaptive to the problem. We don't see how that could at any point really help. So I do not know.
All right, thanks.
Okay, thanks a lot for these questions. And okay, so I see that 1 hour already passed, so I'll be quick. Fortunately, I only have very few slides for experiments. So this is one which just shows that if you run ProxSkip and you run, let's say, Nesterov accelerated gradient descent, then ProxSkip can do much better in terms of number of communication runs, even though both would enjoy accelerated communication complexity. In ProxSkip, the acceleration comes from local steps. In Nesterov method, it comes from that Nesterov trick. So here is how the methods compare. So these are all the state-of-the-art local training methods compared. And it depends whether you like the comparing in theoretical setup or not. So this is a very fair comparison in the sense of we apply all the hyperparameters as the theory predicts. We don't do any fine-tuning, no cheating of that sort. We run the methods as guaranteed to convergent theory. If we do that, there's a huge gap between ProxSkip and everything else, because we get communication acceleration and these other methods that they don't. So that is very apparent. However, and now I want to jump to this plot on the left. Once you start fine-tuning the step sizes and so on and so forth, then you can see that ProxSkip is really, by the way, we call the ProxSkip SCAFNU here. Okay, so I forgot to say this. So ProxSkip is this red method. And when we apply it to the Federated Learning problem, then we call it SCAFNU, and we call it SCAFNU because there was this other state-of-the-art method before called scaffold, and it was just continuing with fooling around with the names of these methods. So no other reason than that. But okay, there's one more reason. That the one reason is that the methods have almost identical behavior if you really fine-tune scaffold and do take step sizes which are much larger than theory allows. And the reason, as I said, is really because scaffold can be seen as some sort of deterministic version of scaf new, or if you turn it around, scaf new can be seen as some kind of stochastic version of scaffold. So we believe scaffold can also be analyzed in a way that you would see the accelerated communication, but such a paper doesn't exist. So one of you has to write it, I guess. Okay, and these other methods such as FedLin and SLocal GD, they do also pretty well if you fine tune the step sizes. So somehow we had the right methods, we didn't have the right analysis. And that's one takeaway message you can have. Now in this paper, we have another extension to stochastic setup. We can work with stochastic gradients rather than gradients, and then really the same conclusions apply. And then we have some extensions. I can see there's a question somewhere. Christos, so in these experiments, could you please clarify where the heterogeneity comes in the objective? So the heterogeneity comes from, so let's go to the experiments. The heterogeneity is in the fact that these individual functions, so these AIs, BIs can be arbitrarily different vectors and labels. So there doesn't have to be any similarity between these vectors AIs. But in the previous types of analysis, which showed some improvement over gradient descent, these AIs, in some sense, had to be very similar. Now they can be arbitrarily different. In other words, the functions FIs, which are these would be the FI in this case, could be arbitrarily different functions as long as they're all L smooth and the average is strongly convex. Okay, so this affects local smoothness. Yeah, so in our analysis, we don't take advantage of any type of local smoothness. It could be interesting to think about it, but I guess so. Yeah, I guess that would affect local smoothness. Okay, so we have extension to stochastic gradients. We work with quite general notion of what stochastic gradient means. So we don't assume, for instance, only that the variance is bounded by some constant. This, for instance, doesn't really hold for compression or subsampling. So we work with this AC inequality, where the something like the variance is almost the variance is upper bounded by twice some constant times Bregman divergence plus a constant. And this, in fact, for functions which are convex and L smooth is probably satisfied for almost any type of stochasticity you throw at the estimator. We can work also in arbitrary connected networks. So we don't have to work with fully connected networks where one proxy evaluation simply means averaging over the entire graph. We can work with some sort of a partial averaging because of communication just to neighbors. In other words, we can work with the decentralized optimization setup, and we have this already in the ProxSkip paper, but I'm not going to talk about this. And then we have these three extensions. I already mentioned two. So the one that I didn't mention was extension 4, where we can do variance reduction for the gradient estimators on these local nodes, and we can get some nice results of the type that if okay, let me backtrack a little bit. So now that we finally understand that local training leads to communication acceleration, also in theory, we can start asking more refined questions which previously none of the papers asked. And that is this: let's not ignore the cost of local computation anymore, because in all previous papers on local training, the analysis was always shown in terms of number of communication rounds, completely ignoring what happens locally. So somehow people implicitly work with the communication computation model, which said that communication has cost 1 and computation has cost 0. But as soon as we now know that communication really helps in theory, we can start asking a more refined question, like we can assign to communication cost 1 and to computation some cost C, and try to see, can we do better than ProxSkip in the regime? And in fact, we can give positive answer, and we gave positive answer here in this paper. If you replace the local solver from gradient descent to a certain variance reduced SGD method, then we get a more efficient method in this new model of communication and computation. So we have a few more papers in the pipeline, which hopefully will appear online soon, but this is it at the moment. Thank you very much.
Okay, thank you very much, Peter. It's a very nice talk. I'm just going to stop the recording and then I'll take questions?